Did you know that one woman measuring thousands of tiny little dots on photographic plates discovered a way to measure the universe? Her name is Henrietta Leavitt. This story and more in The First Light, now available on Kindle.
Prologue, the maelstrom before dawn, the universe before the first light. For 380,000 years, the universe was a prison of light, not darkness. Light, brilliant, blinding, violent light. The newborn universe was unimaginably hot, millions of degrees. Every cubic centimeter was a maelstrom of photons, electrons, and atomic nuclei, colliding billions upon billions of times every second. There was no silence, no empty space. Every instant was a riot of collisions. Light was everywhere, yet no light could travel freely. Every photon that tried to move was almost instantly scattered by a free electron, thrown in a new direction, then scattered again and again and again. The universe glowed with the brilliance of a star, yet paradoxically, nothing could be seen. There were no stars, no galaxies, no planets, no sky, no horizons, only an endless ocean of incandescent plasma. For 380,000 years, light was trapped. But the universe was changing, it was expanding, and as it expanded, it cooled, not in minutes, not in years. Over nearly 380,000 years, the temperature fell from millions of degrees to just a few thousand. Slowly, almost imperceptibly, the chaos began to subside. Then came one of the most extraordinary moments in cosmic history. For the first time, an electron drifted toward a proton. For hundreds of thousands of years, every attempt to form an atom had ended the same way. A passing high-energy photon carried enough energy to tear the electron away almost immediately. The universe had simply been too hot, but not anymore. Its relentless expansion had cooled the cosmos just enough. The electron was not torn away. It stayed. The first stable hydrogen atom was born, then another, then trillions upon trillions more. Across the entire universe, everything changed. The dense cosmic fog of free electrons disappeared. The universe became transparent. The light had not been created that day. It had been trapped. Now it was set free. For the first time since the beginning of time, photons could travel freely across the cosmos, across the entire universe. Ancient light began racing through space at the fastest speed nature allows, 299,792 kilometers every second, a journey that continues to this day. Those photons have never stopped. For billions of years, they crossed an expanding universe in silence. As the universe expanded, space itself stretched. Those ancient photons stretched with it. What had once been brilliant orange-white light slowly slipped beyond human vision. Their wavelengths grew longer. Their energy fell, until billions of years later they had become faint microwaves. Meanwhile, the universe continued to change. Gravity gathered the first hydrogen atoms. The first stars ignited. Inside those stars, new elements were forged. Those elements built planets. On at least one of those planets, chemistry became biology. Biology became consciousness. And consciousness looked back at the sky and asked the oldest question of all: where did we come from? For countless generations, humanity simply looked at the heavens. Then it learned to preserve the light, to measure it, to separate it into its hidden colors, to ask it questions. Each generation built better eyes. Each generation learned to read the light a little more clearly. With every new question, the universe revealed another of its secrets. Eventually, those same ancient photons, released when the universe first became transparent, reached a small rocky planet orbiting an ordinary star in an ordinary galaxy. There, humanity built instruments capable of detecting them. Astronomers would call this ancient light, the cosmic microwave background. It is the oldest light in the universe. It is the furthest back in time that light can ever carry us. Beyond this moment, the universe becomes opaque once again. No telescope will ever see farther. Everything that came before must be reconstructed, not from light, but from physics, from mathematics, and from the remarkable ingenuity of the human mind. The universe had written its story. Humanity was about to learn how to read it. This is that story. Chapter 1. Measuring the Universe. Can I borrow your 138 trillion kilometer ruler? For thousands of years, humanity looked up, The stars inspired wonder, they guided travelers, marked the seasons, inspired myths, but no matter how carefully astronomers observed the heavens, they faced a fundamental limitation. They could see the stars, but they could not measure the universe. The human eye is a remarkable instrument, yet it forgets. A night's observations disappear with the sunrise. The faintest stars escape its notice. Subtle changes are easily missed. Even after the invention of the telescope, astronomers still relied upon careful sketches, careful notes, and extraordinary patience. Then, astronomy entered a new age. For the first time, light itself could be preserved. Photographic plates transformed astronomy. Instead of relying upon what an astronomer could see in a fleeting moment, a telescope could gather light over long exposures. Fainter and fainter stars slowly appeared on the plate, and when the exposure ended, the observation remained. The stars no longer vanished when dawn arrived. Their light could be studied, measured, compared, night after night, month after month, year after year. A permanent archive of the heavens began to accumulate. Astronomy was no longer simply the art of observing the stars. It was becoming the science of measuring their light, and hidden within those enormous collections of astronomical data was a discovery that would change our understanding of the universe. My name is Henrietta Swan Leavitt. I worked at the Harvard College Observatory. Ironically, I rarely looked through a telescope. My work began after the observations had already been made. Boxes of photographic plates arrived from observatories around the world. Each plate was a frozen moment in time, a permanent record of the night sky. While others saw photographs, I saw measurements waiting to be made. Day after day, I compared plate after plate, searching for stars whose brightness changed with time, thousands upon thousands of tiny points of light, measured, recorded, compared, then measured again. Today, we might recognize this kind of work immediately, an enormous collection of data, and someone searching within it for a pattern. But there were no computers, no algorithms, no enormous digital databases. There were photographic plates, a measuring instrument, a pencil, and the human mind. Most people would have seen thousands of tiny points of light. I saw patterns and patterns change everything. Graphic plates I studied came from the small Magellanic Cloud, a nearby galaxy containing hundreds of thousands of stars. Because those stars were all approximately the same distance from Earth, their apparent differences in brightness could not simply be explained by distance alone. That made the small Magellanic Cloud the perfect natural laboratory. One by one, I measured the changing brightness of hundreds of variable stars. Most changed unpredictably, but one particular class of stars behaved differently. They brightened, then dimmed, then brightened again, over and over. Each possessed its own remarkably steady rhythm. Some completed a cycle in only a few days, others took weeks. These remarkable stars became known as Cepheid variable stars. And then I noticed something. The brighter Cepheids had longer periods. The fainter Cepheids had shorter periods. The relationship was unmistakable. The rhythm revealed the brightness. And if you knew how bright a star truly was, you could compare that with how bright it appeared from Earth. The difference revealed its distance. Hidden within the rhythm of these stars was a way to measure the universe. They had become our cosmic ruler. For the first time, humanity possessed a ruler long enough to begin measuring the vast distances between the stars. At first, its reach was modest. Nearby stars, then star clusters, soon entire galaxies. My discovery did not reveal the size of the universe. It made that discovery possible. Others would take this new ruler and measure farther than I ever could. One would reveal the true size of our own Milky Way. Another would discover that the spiral nebulae were not clouds within our galaxy, but galaxies of their own. Others would discover that those galaxies were moving, together. Their discoveries would transform humanity's understanding of the cosmos. But none of it could begin until humanity learned to turn starlight into measurement. The photographic plate had given astronomy a new way of seeing. The patterns hidden within those plates had given us something more, a way to measure the universe. One question had been answered. Another immediately appeared. How large is the universe?